The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Mehdi Moradllo from Oregon State University will present settlement of fresh concrete using neutron radiology to quantify the influence of mixture proportions.
Thanks, Ruzbe, for the introduction. Hello, everyone. My name is Mehdi Khanzadeh. I'm a postdoctoral research associate at Oregon State University. So today I'm going to talk about the settlement of the fresh concrete, and we're going to use the neutron radiography to quantify the influence of the mixed proportions. So the outline, I will have a brief background, then I will talk about the methodology, result, and discussion at the end, concluding remarks. So what are the causes of the cracking in a fresh concrete? I listed here 3 main causes. The first one is the rapid evaporation. It happens when the evaporation rate is higher than the bleeding rate, and then we start forming the capillary meniscus at the surface, and then capillary pressure, which causes the crack as shown in this image at the bottom. The second one is the autogenous shrinkage. It happens especially in low water cement ratios because of the smaller fine pores and the high pore pressures. And the third one, which I'm going to talk more about today, is a settlement when aggregate and cement grains are settled down because of the gravity, and the water moves up, and then in the areas of the non-uniform settlement, for example, around the cracks, then we will have a cracking. Sorry, around the rebar, we will have a cracking. So what methods are previously used to kind of study the settlement? I categorize them in 2 different groups: the single point measurements as shown at the left side, displacement of the, for example, steel pin resting on the surface of the sample, or nylon ball movement, or strain gauges at the surface. And also we have multiple point measurements, for example, a non-contact laser measurement as shown at the image at the right side. So, but the method today I'm going to talk about and introduce to measure the settlement is a neutron radiography. So the basic concept is similar to the X-ray measurement or X-ray radiography, but instead of the X-ray beam, we have a neutron beam. As shown at the right images, I have a concrete cross-section imaged by using X-ray at the top, and the same cross-section imaged by neutron at the bottom. So over here at the left top image, I'm showing the kind of the cross-section from the beam line. So I have a reactor over here, then I have a neutron beam passing through the this lines, and then gets to the object, and some of this neutron beam gonna attenuate it in the sample, and some pass through the sample, and then we have a detector at the back to capture the images. So by comparing the initial intensity of the neutron beam and the final at the detector, we can kind of get and measure the attenuation coefficient for different materials and samples. So today I want to point out 2 main advantages of the using a neutron imaging. The one is a high spatial resolution compared to the previous methods I presented, and the other one is a high interaction or cross-section of the neutrons with the hydrogen atoms, which enables us to use this method to study the water distribution inside the sample or water movement inside the sample. So these are the objectives of this study. We want to see if we can use neutron imaging to study the settlement and see the influence from the water cement ratio on fresh settlement, and see the impact of the water reducer admixture. So if you want to use the low water cement ratio and add a water reducer to kind of increase the workability and slump, how it's going to change the settlement. And then the impact of the conditioning, we're going to have a sealed versus drying case. And at the end, we have the influence from the rebar on settlement. So here's the plan view of the reactor we have at Oregon State University, 1.1 megawatt research reactor. So as you can see here, we have this neutron radiography facility. We have a chamber to control the temperature and RH while testing the samples, and we have a detector system at the back to capture the images. So here's the chamber I was talking about. So this is the chamber, and this is the detector system we have. And here's the inside the chamber. We have a moving table to move up and down and right and left. And in this case, I'm going to use the Teflon molds because they are not reactive with the cementitious materials, and also they are almost invisible in their neutron beam. So if I want to measure the water content inside the sample, I have to kind of calculate the water attenuation coefficient in the beam line. In order to do that, I'm going to use these cells here, the water cells, moving from the 1 millimeter to the 5 millimeter thickness, and then these are the results. At the y-axis, I have the measured intensity difference, and at x-axis, I have the water thicknesses. So the slope of this line, by using this equation, the Beer-Lambert law, we can get the water attenuation coefficient. In order to account for the impact from the mixed components, for example, sand or cement, we kind of did the same experiment in front of the oven-dried samples with different water-cement ratios, and the results are shown here. So the experimental program, we tested 3 different water-cement ratio, 0.36, 0.42, and 0.5. And in case of 0.42 and 0.36, as shown here, we use the water reducer with different dosages to increase the slump. And we measured the slump with using a mini slump as shown at the right image. So we use the vacuum mixer to prepare the mixers, and as I said, the Teflon molds to cast the samples. So the conditioning, we condition the samples at 50% RH and 25 C temperature. And as shown here at the images, we have 2 replicates for drying cases. We didn't do any covering at the surface. And we have a sealed case as shown at the bottom right image. We kind of seal the samples with aluminum tape at the surface. And we have a case, we embedded a rebar inside at the middle of the Teflon molds as shown at the bottom over here. And we use the number 3 rebars in this case. So imaging was started 5 minutes after casting the samples. And also we had a plastic targets at the surface of the samples in order to kind of trace the movement of the plastic targets and compare with the settlement of the surface of the sample. So here's the brief overview from the image processing. First step to background correction by using a flat field and dark field images as shown example here by using this formula. And the second step is we can get the mass change profiles from this method by high resolution. So for mass change, I'm calculating the water thickness at different location or at different pixels as shown here. And then I can calculate the volumetric water content, and I can change to the mass at different pixels as shown here. These are the examples of the images. I have 0 minute as a reference image, and then I have a 5-hour or other time series images. Then I can normalize these images based on the 0 minute and get this difference. The area here is a dark area. It shows the settlement. And this is how the kind of mass changes inside the sample. And this is how, based on these formulas, I can get the profile for the mass. This is the surface of the sample, and then go down to the bottom. So we can get kind of by using the area underneath the those curves I showed, we can get the cumulative mass change results as shown here, for example. So the blue dots showing the results from neutron, and the red dot here showing the results from gravimetric method. As you can see, they are matching perfectly, and it shows the reliability of this technique. So as I said, we can normalize the images at different times. For example, I'm shown here 10 minutes, 1 hour, 5 hours, and these are the settlement at the surface, the dark spot. So we can kind of quantify this area, and we can get the settlement at the y-axis versus the time at the x-axis. So let's move to the result. This is example of the mass profiles with, for different water-cement ratio in the drying case. And you can see that we have really high spatial resolution around 80 micron. And here's the sealed cases. You can see in the sealed cases, we almost have no change in the mass, which is kind of expected. So here's the cumulative mass. As I say, we can measure from those curves. And as you can see, we at the left side, drying case, at the right side, the sealed case. And in sealed case, we have no mass change in the samples. So I want to more focus on the settlement for the rest of the slides. So here's the settlement for the different water-cement ratios in the drying condition at the left side, and for the sealed case at the right side. So if we move from the 0.42 water-cement ratio to the 0.5 water-cement ratio, I'm getting around 120 to 150% increase in the settlement. So why this happens? This is because of the high permeability of the mixture at the fresh state. I'm going to talk more about this in the later slides. So how about the sealed case versus the drying case? As you can see, we have around 40% decrease in the sealed samples compared to the drying condition. So why this is happening? This is because we have less evaporation, we have no evaporation, and also the bleeding water reabsorb inside the pores, and we have less pore pressure and then less settlement in this case. So I'm going to move to the settlement in case we use the water reducer. At the left side, I have a 0.42 mixes with adding a water reducer, and a comparison with the 0.5 water cement ratio. At the right side, I have a 0.36. So if we compare the 0.42 mixture with a water reducer, and the case we have almost similar workability or slump for the 0.42 with a water reducer compared to the 0.5, we have around 100% increase in the settlement, and it's the same for the 0.36 one. So this shows when we are adding a water reducer to the system to improve the workability, it's not changing the settlement or impacting the settlement significantly. So this is the similar trend for the sealed samples, and I'm going to talk more about why this is happening in later slides. So this is so let's dig in and see what's really happening here. I have the slump versus the water cement ratio. The black line is showing the control sample. It means we didn't use any water reducer inside the mixes. And the red dot over here is showing when I add a water reducer to reach about the same level of the workability as 0.5 here. And the blue shows I added even more to have higher workability compared to the 0.5 mix design. So let's compare this to the settlement results. As you can see, I have about 80% increase in the slump over here. I'm just comparing the red dots. And over here, just in the settlement case, we have 9% increase. Again, this shows the impact of the water reducer is not significant on the settlement. The same trend for the sealed sample over here. And so really what's happening, and here is in the left side, I'm showing a cartoons for a case with a low water cement or low water to solid contents, and also I have a high water to cement content. So as you can see, we have less space in case of the low water cement ratio to settle, but it is not the case in higher water cement ratio. So if you want, so we can say settlement is a function of the permeability, and then it's function of the water to solid ratios. And if you want to compare this to the theory, for example, one-dimensional small strain consolidation theory, which is approved by Kuak et al., is applicable for the concrete and mortar settlement, we have this differential equation relating the pore pressure to the coefficient of the consolidation. And really, this term is a kind of related to the coefficient of the permeability of the mix, which we can say that's why when we have a higher water to solid content, we have higher permeability than we have a higher coefficient of the consolidation. But in case of the adding a water reducer, really we are not changing the permeability of the mix design. We are just dispersing the cement particles to have higher workability. So I'm just going to briefly talk about the impact of the rebar. As you can see here, we have around 10% reduction in when we are using a rebar on the settlement. So here's the other observation on the rebar, which is interesting. The accumulation of the free water around the rebar we capture at the fresh states, as shown here at these images. And over the time, we can see it's kind of dries out or moves toward the pores of the sample. So here's the more quantification. I selected the area close to the rebar at the edge of the rebar, and also I select the area away from the rebar. And here's the quantification, what is the water movement. As you can see, in case of the area close to rebar, we have higher mass movement or water movement in this case. So quick summary and conclusion. As I said, the settlement increased by 120% when I use 0.5 instead of 0.42, and this happens because of the higher permeability of the matrix. And sealed samples showed about 40% decrease in the settlement, and that's because of the reabsorption of the bleeding water inside the pores and kind of reduction in the pore pressure and the stresses. This can be the main conclusion from this study. Adding water reducer to increase the workability has no significant impact on mortar settlement. Or we can say if you want to limit the slump just because of the settlement, probably it's not a good idea, results showing this. And also we saw the free water accumulation around the rebar, and this moves to the pores over the time. And as you can see, the neutron radiography is a really powerful technique to use for measuring the settlement and also the movement of the water inside the sample with high spatial and high temporal resolution. With that, I would like to acknowledge the operation team at Radiation Center, Oregon State University, and my undergrad helper, Mitch Keys. And thank you for your attention, and I'm open for easy questions.
You evaluated only number 3 bars.
Mm-hmm.
What about if you increase the size of the bar? Because what's really important there is a differential settlement. Do you think it will increase the settlement if you have a larger obstruction? Or
So really we didn't test it, but because of the limitation in the space. But we can test it like if we make a really larger molds to see if it's impacting or not. But if you can see, so the phenomena is we are getting a settlement, and in area of the non-uniform settlement we will have a cracks. But our main goal to show that if we use like water reducer and to increase the workability, how it's going to change the bulk settlement, and it's kind of indication of your cracking that happen, right? If it's susceptible to cracking or not. So that's the main goal.
For one water cement ratio, how many samples you have tested?
So for dry, we have 2 replicates. Yeah.
okay.
What's the focal spot size of the detector?
We have the resolution, the spatial resolution around 80 micron. We have other system to kind of go down to the 25 micron, but this is faster, so that's why we are using this one, detector system.
Okay, let's thank Mehdi for the presentation.